Thanks for coming to our talk. This is John work with Pierre Jubilo, Sylvain Ristein and Dorian Desblanc. And the work we are presenting today was started by Pierre as a part of a French project, with one core goal of studying mechanically verified program semantics in the context of real-time digital signal processing languages. In particular, we are interested in the intersection of DSP, or digital signal processing, with programming language techniques and interactive theorem proving. To this purpose, we have developed a calculus, W, based on the synchronous programming paradigm, which serves both as a base for the development of a programming language and the verification of DSP algorithms. KDC constraints for W are convenience, efficiency, a fully formal mechanized specification, and adoption of standard techniques from the field, such as logical relations or co-effects. Moreover, we'd like to achieve all of this while keeping a lightweight footprint. For example, we shouldn't pay a large price for our desire to encode W in a fully mechanized setting, or in order to make the execution model efficient. In the rest of the talk, we will discuss the language, its semantics, the mechanization of non-trivial properties, and its execution model. First, we introduce some basic digital signal processing notions. We follow the excellent free books by Julius Oren Smith III as our main reference. The relevant concepts we need are signals, which we represent mathematically as functions from positive time to a sample type R, filters, which are functions from signals to signals, and last but not least, a typical property, linear time invariance, which states that a filter admits a linear decomposition, a quite important property in DSP. Filters are often defined in a diagrammatic form. Scaling is represented by triangles, in this case scaling by the coefficient B0, addition by round nodes, which take two inputs and one output, and delays by squares, which actually will delay like a memory cell and will delay the signal by one sample in our case. In the top figure, in this figure, we see a typical second-order recursive filter. The filter works by first applying a finite impulse phase to the input signal X, then averaging over the signal's past values. Below, we see a different kind of circuit, the wave-guide resonator, often used in physical-based synthesis. This circuit has no input, but a couple of tapping points immediately after the delays, so it's used this way. Even if the diagrammatic form is often used in the DSP world, filters can be expressed in a way closer to functional programming using equations, as shown in the slide. For example, in this case, we define the value for time step m for input signal y is going to be exactly the mathematical expression of this diagram. This is already hinting towards the W calculus. The W calculus is quite minimalistic. Types are either strings of tuples or string functions. Expressions are standard, except for variables, which are indexed with a time offset k. The time offset k offers the programmer the capability to access the k past values of a variable x, which is similar to the pre-operator found in synchronous languages, but in our case, restricted to variables. A classical delay operator can be recovered in our setting by applying the expression e to an identity function, but with a delay index in the variable. This already highlights our choice of call-by-value semantics, which we will shortly explore in more depth. Another important point is the behavior of the feedback construction in W. By default, all references to the bound variables in a feedback expression do already refer to their previous value. Thus, we avoid causality problems. For example, in this case, this counter x0 will actually refer to the previous value of the counter. So, for example, at time step 10, this will be 10 value 9, okay, and then we will return 10. Equipped with these tools, we can implement or filter a sample in a quite straightforward way, provided a bit of syntactic sugar to better highlight the structure. In our case, we just first the finite impulse phase for the input is modeled as a simple multiplication in our language, which we add indeed the value of the feedback y. We tap here on the coefficients a. Some of you have likely realized that we could implement this filter using less delays, and indeed, there is a different implementation strategy called the direct form 2. And while mathematically both implementation strategies compute the same function, their numerical properties are quite different in practice due to the floating point error accumulation. As we will see, our semantics are low level enough that these details can be captured. And for just to comment here we can see that we have a feedback loop. Okay, so we compute the values of the feedback that then just we basically can multiply in this case by the previous values of the feedback. Okay, by the previous values of the feedback and the coefficients b. The next example is the white kite resonator. First, we show its mathematical equation, and just below it's encoding into W. Using a feedback over a tuple allows us in this case to expose both tapping points, and a bit of syntactic sugar could render both expressions virtually identical. Once the calculus has been presented, we ought to define its denotational semantics, which we will do using the Coq interactive proof assistant. Coq, or Rooster in French, is a mature, state-of-the-art interactive theorem prover using hundreds of verification projects. Coq takes advantage of the carry-over correspondence to develop a consistent and powerful logical system where proofs are functional programs and types are the theorem statements or propositions. Coq's functional language, Kagina, is pretty similar to Haskell or OCaml. However, it doesn't allow for unbounded recursion as to maintain the consistency of the underlying logic. In our context, the mathematical components library will provide the core linear algebra definitions and theorems. We will take advantage of Kagina to embed W directly inside the prover. While this poses some challenge and requires some extra care, we are quite happy with the overall result. The first step is to represent W syntax in Coq, and for that purpose, we will use a well-known representation technique, well-typed as syntax trees. Thus, the Coq type for every expression will include the gamma and the type of the expression, and this technique allows us to do interesting stuff, such as, for example, return the type for variables using the list nth function, which will return an element, the nth element of a list. In this case, the nth element corresponding to the variable b. Another interesting point is indeed we are going to require, but for lambda application we can encode the typing rule, because lambda is going to have the function type, and application is going to require the first expression has the function type and the second expression has to have the right cardinality. Moving on, the key idea of the denotational semantics is to interpret a string transformer at time k as a function from the full history. So this example is like a size list from the full history of the argument to the value. In this case, we have to include the k-pass values plus the current value, because this is the convention we have used. And once we have that, this will allow for the functions to access, as you can imagine, all the previous values for the argument. Okay, so this is how we are going to interpret our variables. First, before moving to the interpretation for the definition itself, we need to define the environment. So, for example, an environment for gamma at time k is actually a function from the variable, for a variable in gamma, to a tuple indeed with all the right things we need to provide to the value, to all the history of the function. And then interpretation of expressions at time n takes an expression, takes a time k that is less than n, takes an environment, and then it's going to return the interpretation for the expression type, for tau in this case. Then the interpretation transformer S is defined, takes an interpretation for n, and will define an interpretation for the next step. And closing iterating over this S interpretation with an initial interpretation, we can define the global interpretation up to n steps. As we mentioned, the core point, the core machinery here is the step interpretation transformer. So P stands here for the previous interpretation, and this is defined by induction on the expressions or on typing. In this case, as we are using this well-type Astor syntax trees. So, for example, when we want to interpret a variable, when we want to interpret this expression of a variable under gamma on of type R of A, then we just access the environment as it's standard. For example, to interpret a function, we will embed this into a Coq function. Okay. And more interesting case is, for example, for application, what we will do is we will do the interpretation of f, which is going to be a Coq function, and then we will compute indeed for all the UC, for all the previous values up to 0. We will call recursively this interpretation transformer over E. So this is still well founded. Unfortunately, for feedback, induction cannot work. This is where we use the previous interpretation. Okay, and imagine this is the expression a concise representation of the expression is as FB, and then so the interpretation of the feedback is we're going to assign to the environment the interpretation but using the previous interpretation. Okay, and note we need to use the default value for the first value of P, obviously, and this is okay. This is how the code looks in Coq. In this case, the use of implicit parameters makes the Coq code more readable than the mathematical counterpart we just showed in the previous slide. And I think it's quite compact. I dare to say it's quite compact definition for the complexity of this. And in this, we use a couple of helper functions. So, for example, for the application, this will accumulate. Okay, it's passing over this expression, this interpretation, this fixed point, this interpretation expression over the argument, and for the feedback we will accumulate the feedback with the expression P. And then finally, the full interpretation is going to work by induction on M, and then we will use for N0. Then we will use the initial interpretation as 0 that maps everything to 0, and for the n+1 case we can just pass the previous one, and this works fine. And Coq is gonna take this as a well-founded definition. We can validate the semantics in the usual equational way, but we will prove a more advanced theorem, namely that every well-typed W expression is linear in the DSP sense. If you remember from the introduction, F is linear if and only if x and y belonging to the domain of F two streams. Then for all x and y belonging to the domain of f of x minus y corresponds to the decomposition of f of x minus f of y. And well, we're using minus here. You can use addition too if they're equivalent. We're using minus because this is the definition already present in Coq. And to extend this definition informally from the DSP side, is the informal definition for F. We need to, in order for this to work, to prove that every program is linear, we need to extend this to full programs. In particular, we need to extend to programs of all kind of types. And to do that, we are going to define what is called a logical relation, in this case a ternary one, which is actually a relation indexed by the type. Okay, so here tau is a parameter, and it's going to take for a given type tau, it's going to take 3 elements of tau at time step n. This is not so important here, we can fix it for now. And then it's going to tell whether they're related or not. So in our case, for example, for a base type b1, b2, b3 of tuples of samples, they're going to be related if p1 happens to be b2 minus b3. Here minus is overloaded. Coq can overload this to do subtraction over tuples too. And the interesting case and the typical case for a logical relation is the functional case. And in this case, we are going to say that the functions are related if for all. Okay, this is very important. If for all values, okay, for all values of the type of the input type of the function that are related. In this case, we have expanded the definition of related, but we could just, if you want, we could just call this lin RA. Usually this is the way they're done. They're related, then the outputs, they have to be related. And once we have these definitions, then we can move on and prove what is called the fundamental lemma of logical relations. And in this case, we're gonna say that indeed, like assuming we're gonna work over expressions, and this we need to, in order to prove it, okay, we need to work over open expressions. Otherwise, the induction is not gonna go through. And then for all environments, we're gonna say the environments are related to. We can extend our definition of related to environments. In this case, it's just this addition. And then if environments are related, then we're gonna say, in this case, for any expression of type tau, then the interpretation, okay, the interpretation over a P is going to be related for the same expression E. Okay, so in this case we have, you see, we're interpreting E under gamma 1 has to be related to the interpretation of E under theta 1, theta 2, and theta 3. And by the way, P also, there is a small condition here, and this previous interpretation is that this previous interpretation has to be linear. Okay, which is actually a straightforward definition. It's actually that respect this condition itself. And indeed, for example, this definition, if you unfold it, it implies, for example, for a function in the empty context, it implies the usual definition of linearity. And we can unfold and then substitute, and then we're going to have that indeed we have that for all input value. Okay, if you remember from the previous slide, for all this input value, we have just replaced big1 by this. For all these input values, this is equivalent to this. And this corresponds, this matches the thing, and we have completed proof. We can see the proof in Coq, and actually we think we are quite happy with the way this has worked, and it's more or less a transcription. Here we have this environment additive, it's just a relative, it's just the logical relation, and this is the step transformer, and everything works as stated with this, actually with this condition, and we just need to do an induction. This we can prove by induction on dispersions. And then, okay, we need to do another induction on the number of steps, which is quite trivial once we have this, to prove that the full interpretation is linear. And from this we obtain the corollary in the paper. Okay, and we can instantiate with W programs, we can instantiate the usual definitions of linear algebra in Coq. We're approaching the end of the talk, and we will conclude with an overview of the efficient execution model we have developed for the W calculus. And indeed, the semantics we developed in the previous section are very convenient for proving. They are very easy to understand. It's that we have a function, and then we pass all the pass values of the arguments. This allows us to dispense of bound conditions and many other things. But of course, this in practice, this has several problems. First is unbounded, and second, as defined, it requires to recompute all of the pass values of every function application. So it doesn't take a lot of effort to think what the complexity of this is. Not good. So indeed, we are going to work under the assumption that a function is going to only access a bounded number of pass values, which we call D here. How do we compute this is not important here. Okay, we will assume that for every function we can compute this value, which in practice we can with our setting, using some tricks. And then once we have this, we can only limit what we are passing to the function to a finite number to a bounded number of values. And the second step that we can make to improve this is actually to memorize. Okay, so when we are computing, once we have computed in the application, we have computed all the pass values of A here. In the step n+1, in the time step n+1, we can just reduce all the previous one and using a circular buffer and just then compute the next one. This will give us the efficient model we're looking for. In order to implement this, we need to modify a few things. For example, our environments now are going to be maps from variables to pointers to the heap. The heap is going to have is going to store like a buffer, D values for a particular buffer. It's going to store the number of values used of the corresponding type, and then the heap is just a map from the pointers of type tau to well-type pointers to well-type buffers, and similar to what will be OCaml arrays. And then we need to update the syntax to take this into account. In particular, for every function application now, for every application that we need to add a pointer. We're using this arrow to signal that actually we're going to store into the buffer. Into the buffer, we're going to store the value of E at this current type. And also for the feedback, we need to add a pointer to all the feedbacks. It's very important these pointers are independent. That is to say, we're not reusing pointers. Otherwise, the semantic will be incorrect. And the location, process, and the bound calculation belong to the front end, so from now on we will assume that they are properly allocated. So we can encode this imperative machine in OCaml. As we're moving towards more practical evaluation of our calculus, we want to take advantage of the faster speed and imperative capabilities of OCaml. And indeed, our machine is going to take an expression that of type A. We still use a bit of dependently type encoding, in this case in the form of generalized algebraic data types. This is very convenient. And then the machine is going to take an environment with the pointers, an expression of type A, and it's going to return a type A. Okay. And for example, for the lambda case, it's going to return a function that takes a pointer and then puts the pointer in the environment and calls and evaluates the expression E. For variables, it's going to look up the pointer, the corresponding pointer in the environment, and then from the pointer look on the heap. And for application, this is much more interesting now. So here, as you remember of the update syntax, we have a pointer for every application node, and then what we are going to first do is we're going to compute the current value for the argument expressed in A, and then we're going to shift, we're going to shift the buffer that we're memorizing. We forget the last value, the oldest value, and with this new value, and then we just call the machine for f. Okay, and passing, of course, this is going to evaluate to a function, and we pass pointers, like kind of higher order construction here. Feedback is exactly the same. And then just this automaton is the only thing we need to do. We need to initialize the buffers with 0, allocate the buffers correctly, and then we can just evaluate this. It's just repeating this automaton, in this case 1 by 1, but we could also vectorize or do some more advanced applications, and then we will evaluate the program. Unfortunately, this is still not enough as to have code that could compete with DSP languages. Okay, the interpreter does not recompute previous step. This is a very obvious problem, but it is far from running in constant memory, which is usually required due to closures and the interpretation overhead, in particular for the lambda case. But we could alleviate this writing a full compiler, but we've been a bit lazy here, and what we're going to do is we're going to stage our interpreter, and this way we will produce a specialized version for every W program that will run pretty good, as we're going to see. And then what we do, thanks to, we have this encoding of the GDT, etc., plus the OCaml optimizing compiler, and then we're going to get a code that actually, this was an experiment to see how good this code can be with this very, very easy effort, and actually it was not bad at all. This is the design interpreter stage. This is a bit more complicated. Here we have add constants, it's a bit richer language. And okay, you see, we need to. This is typical staging. Okay, so this is quote and unquote operators. Okay, but the fact is, for example, like this will indeed, as a program structure is static. This is very important. It's a kind of data flow language in a sense. This will produce indeed like a very specialized program for every filter, for example, like totally free of any interpretation overhead. And these are the results. So basically we are comparing like the basic is like the interpret code, okay, which already is not bad. For the interpret code, I have to say it's pretty good. Then this is the meta-OCaml code, and this is the handwritten code. And actually we can see even in one case, the generated code by this approach is faster. In this case of a simple feedback of order 15 filter, and this will be feedback plus finite impulse response. And this is allocation. So actually we have to say this is pretty encouraging. Of course, this is just an experiment. This is not in any way production ready, but this is pretty encouraging. Like this compilation strategy, it is kind of this model actually. I think compared to this handwritten code, it tells us that actually we're on the right path. If we want this calculus to be a base for a compiler for DSP programs that is going to be efficient. And well, this is the end, and thank you very much. And there is a few interesting things still. Most of the things here are for future work. For example, the front-end deserves another paper because there is some bidirectional typing. There are coeffects. This is how we compute the bounds of the use of variables. There are like regular functions. I mean, not synchronous functions that are used, for example, to define like top-level constants, etc., etc. There is the buffer allocation that itself is pretty interesting. We have an equivalence proof which is already pretty advanced for an imperative machine. We hope to publish soon too, and requires a technique similar to other techniques used in synchronous languages, like recently, not long ago. Regarding how do you capture the invariance of the buffers. We also have a proposal for a multi-rate semantics and a multi-rate processor. We have also an advanced typing system that allows us to view variables as arrays. So it gives you a bit more expressivity. We have actually a bit of prototype of the functionalization to produce a C code from this language. And there is also many practical issues to research that for DSP writers, like modules, initialization of systems, randomness. And also we mentioned in the paper, you can read all the details in the paper and in the GitHub repository, and there is a lot of related work. We tried to be quite comprehensive with, we couldn't cover everything, but we tried to refer to the main points of inspiration. So that's all. Thank you very much, everybody, and we'll be very happy to take questions.